make their food really fast these days. Hey, that's a cool idea. I'd like to start a fast food chain with 2 stations making French fries and burgers. Now, each of these stations can be run for a certain amount of time. I don't want to overwork them, so I'm going to run them for different periods of time. Now, with the sale of each burger or each packet of French fries, I'm going to make some profits. Different profits, of course. Now, how do I maximize the profit from this venture? Let's check it out.
Hello and welcome to Math 12, where we help you to maximize those important scores while minimizing your troubles. Hi, I am Shankar, your personal guide to this wonderful world of mathematics. You see, this world is full of choices and constraints. Now, deciding about your best strategy forms an exciting discipline of mathematics called optimization, which is what we are going to discuss today. In today's episode, we shall discuss what linear programming is and formulate a few important problems on this wonderfully colorful topic. And finally, supply you with enough pointers to tackle those exams. Let's begin today's episode with an appetizer. You see, starting a fast food chain is really not a bad idea. But raking that much profit, definitely a tough job. To make our lives simpler, let's lay out the numbers. At my fast food joint, there are 2 stations A and B. Now, burgers take 2 hours at station A, while French fries take 4 hours. And at station B, burgers take 6 hours and French fries take 2 hours. Now, station A is available for 16 hours in a day and station B for 20 hours in a day. Now, the profit I expect to make is 3 rupees on a burger and 5 rupees on a packet of French fries. Okay, but we know that the equation 3x plus 5y is equal to 7, let's say, is a line in the 2-dimensional plane. However, if the equality is replaced by an inequality, let's say 3x plus 5y is less than or equal to 7, then we have a region that obeys this equation, which is now called a linear inequality. Now, the process of finding the best-in-class solution of a linear function that is subjected to a bunch of linear inequalities is called, you guessed it, linear programming, or LP for short. So why did I bring this up? Remember my fast food joint? In my fast food joint situation, we have nothing but a problem on linear programming. Linear functions are usually used to solve problems that are related to costs, profits, or any other quantity that has to be maximized or minimized and are subjected to some constraints. Now, as a fast food chain entrepreneur, what is my biggest problem? Maximizing profits. Now, the profit is a function of how many burgers and how many French fries packets that I sell. Now, if X is the number of burgers produced and Y is the number of French fries packets produced in a given day, then our objective is to maximize the profit from their sales, which is rupees 3 times X for the sales on the burgers plus 5 times Y for the sales on the French fries. Now, this function is called the objective function for the LP. It's important to note that both X and Y are non-negative because there's no meaning to produce negative numbers of these items. So, X is greater than or equal to 0 and also Y is greater than or equal to 0. These are called non-negativity constraints. So, the total time taken at station A to produce X burgers and Y French fries is 2X plus 4Y. Now, this must be less than or equal to the total hours available at station A. Therefore, 2X plus 4Y should be less than or equal to 16. Now, similarly, for station B, we have 6x plus 2y less or equal to 20, the total number of hours available. Now let's try formulating the LP problem, shall we? We have to maximize the profit, which is 3x plus 5y, subject to 4 constraints. We have 2x plus 4y less than or equal to 16, 6x plus 2y less than or equal to 20, and the non-negativity constraints, which is x greater than or equal to 0 and y greater than or equal to 0. Well, it turns out that the problem may either have plenty of solutions that satisfy the constraints or none at all. In this area of optimization, it is of paramount importance to formulate the problem correctly. There are many software packages available these days to solve such problems. Hypothetically, if the burger costs 25 rupees and a packet of French fries costs 30 rupees, then the total cost of producing X burgers and Y French fries is, you guessed it, 25x plus 30y. Now I can subject this to the same set of constraints, but my objective will be to minimize the cost. Right now, we have a caller who has a question. Let's find out, shall we?
Hello, sir. I thought that this chapter was one of the easiest. But despite getting the correct solution, I keep on losing marks. And I have no clue why. Please help.
That was a good question from Parul. But you know what? You're not the only student who has come across this dilemma. In mathematics, I'm sure that we all want perfect scores, and we need full marks on each question. So we will really tackle Parul's issue, and in turn ours, just after a short break. So stay tuned. Hi, and welcome back to Math 12. Here we help you derive maximum pleasure from mathematics with a minimum amount of stress. And I'm Shankar. I'm here to take you on an exciting journey through the world of mathematics and beyond. In today's episode, we are trying to formulate linear programming problems. We're not going to solve them because even formulation is very important, and I'd like to stress that. Before going into the break, Parul asked me as to why, despite getting at the right answer, she failed to score maximum points in this subject. Well, frankly, when I was in school, this issue bugged me just as much as it is bugging you now. The answer, however, is simple. We need to follow a few careful steps. To give them due regards, examiners allocate each step certain weightage. So, not just the solution, but the steps used are equally important. The journey, as you would agree, is just as, if not more important than the destination. So, if we identify every step while solving problems in LP, we shall have something like step number 1. In every LPP, that's a nice short form for linear programming problem. Certain decisions are to be made. These decisions are represented by variables known as decision variables. Now, these decision variables are those quantities whose values had to be determined. They vary over a certain range. So first, identify these variables and denote them by x1, x2, x3 and so on. Step number 2, identify the objective function and express it as a linear function of the variables that we introduced in the step 1, those decision variables. Step number 3, in an LPP, the objective function may be in the form of maximizing profits or minimizing costs. So after expressing the objective function as some linear function of the decision variables, we must then identify the type of optimization, which is, are we maximizing or are we minimizing? Step number 4. This step is highly important and very fault prone. Identify the set of constraints which are stated in terms of decision variables again, and express them as linear inequalities or equations as the case may be. Now let's try using these distinct steps to solve a few questions. Now to really understand any concept in mathematics, you should try out a few problems. And we've got so many steps right now. What we are trying to do here, if you remember, is to actually formulate the problem and then we'll worry about the solution later. See, in real life, dietitians have to deal with a lot of variables. But then the problems themselves become complicated. So we have to try out a simpler version. So here it is. You see, a dietitian wishes to mix two types of food supplements in such a way that the vitamin content of the mixture contains at least 8 units of vitamin A and 10 units of vitamin C. Now, food supplement 1 contains 2 units per 100 grams of vitamin A and 1 unit per 100 grams of vitamin C, whereas food supplement 2 contains 1 unit per 100 grams of vitamin A and 2 units per 100 grams of vitamin C. Now, it costs rupees 5 for 100 grams of food supplement 1 and rupees 7 per 100 grams of food supplement 2. How does she minimize the cost of such a mixture? Now let's formulate this problem now. Note that all quantities are expressed in 100 grams. Let the dietitian mix X 100 grams of food supplement 1 with Y 100 grams of food supplement 2. Clearly we have non-negativity constraints, which is X greater than or equal to 0 and Y greater than or equal to 0. It makes no sense to mix minus 100 grams, you see. Now 100 grams of food supplement 1 costs rupees 5, whereas the same amount of food supplement 2 costs 7 rupees. Therefore, the total cost Z of this mixture is rupees 5x plus 7y. Now remember, one is costlier than the other, so we have to be careful, right? Now 100 grams of food supplement 1 contains 2 units of vitamin A. Therefore, X times 100 grams of supplement 1 contains 2x units of vitamin A. Similarly, Y times 100 grams of supplement 2 contains Y units of vitamin A. So in the mixture, you will get 2x plus Y units of vitamin A. But the minimum requirement of vitamin A is, remember, 8 units, which means we must have 2x plus Y should be greater than or equal to 8. Remember your inequalities. Similarly, the total amount of vitamin C in the mixture is given by, you guessed it, x plus 2y units, and the minimum requirement of vitamin C is 10 units. So we must have x plus 2y is greater than or equal to 10. We are now in a good position to state the LPP. Minimize. The emphasis is on minimizing. Z is equal to 5x plus 7y. Subject to the constraints, 2x plus y is greater than or equal to 8 and x plus 2y is greater than or equal to 10. We also have the non-negativity constraints, which are x greater than or equal to 0 and y greater than or equal to 0. Now let's take a look at another concrete problem. A company makes two kinds of leather belts, A and B. Belt A is a high quality belt and belt B is of lower quality. The profits, as you guessed, would be higher for the high quality belt, rupees 40, and rupees 30 for the other belt. Now each belt of type A requires twice as much time as a belt of type B. And if all the belts were of type B, the company could make 1000 belts per day. The supply of leather is sufficient for only 800 belts per day, both A and B, that is. Belt A requires a fancy buckle and only 400 such buckles per day are available. There are only 700 buckles available for belt B. Now, what should be the daily production of each variety of belt? Formulate this problem as an LPP. Also, log on to www.topperlearning.com for more questions, exam tips, traps, and much more suggestions. For now, let's take a break. Hi and welcome back to Math 12. Here we help you optimize your comfort level with mathematics and maximize your scores. I'm Shankar and I'm sure that you've been able to solve the problem that I left you with just before going into the break. Let's solve this problem together, shall we? Suppose the company makes X belts of type A and Y belts of type B per day. Remember? Luxury belts are A and regular belts are B. We then need to maximize the profit. Z is equal to 40x plus 30y. 40 rupees profit for every sale of belt A, whereas 30 rupees for every sale of belt B. It's given that 1000 belts of type B can be produced per day, and each belt of type A requires twice as much time as a belt of type B. So, 500 belts of type A can be made in a given day. Therefore, the total time taken in preparing X belts of type A and Y belts of type B is simply X over 500 plus Y over 1000. Now, from our initial plan, the company manufactures X belts of type A and Y belts of type B in a given day. Therefore, X over 500 plus Y over 1000 is less than or equal to 1. In other words, 2x plus y is less than or equal to 1000. Now, since the leather supply is sufficient for only 800 belts per day, we have x plus y, total number of belts, is less than or equal to 800. It is given that only 400 fancy buckles for the luxury belts of type A and 700 buckles for type B are available in a given day. Therefore, we have the constraints x is less than or equal to 400 and y is less than or equal to 700. We now are ready to mathematically formulate this given LPP. We have to maximize z is equal to 40x plus 30y, subject to 2x plus y is less than or equal to 1000, x plus y less than or equal to 800, x less than or equal to 400, and y less than or equal to 700. Don't forget the non-negativity constraints. We have x greater than or equal to 0 and y greater than or equal to 0. It makes no sense to produce negative numbers of any belt. Now let's do a quick recap of whatever we have discussed today. We described the setting of linear programming problems with these observations. 1. If C1, C2, so on till Cn are constants and x1, x2, so on till xn are variables, then the linear function z is equal to c1x1 plus c2x2 plus so on till cnxn, which is to be maximized or minimized, is called the objective function. Inequalities or equations in the variables of an LPP which describe the conditions under which the optimization, namely maximization or minimization, is to be performed. They are the constraints. Now, constraints may be of three different types: less than or equal to something, equal to something, or greater than or equal to something. Well, I'd now like to give you some exam tips, tricks, and possibly go over some traps. I welcome you all to our most favorite exam section. Today we have with us a very important guest who's going to boost your confidence by giving you more insights. Let's hear our guest, shall we?
This is a very important topic from examination point of view, and almost every year there is a question for 6 marks. This topic deals with real life and can be solved by expressing the problem as a linear inequation or as quadratic equation. The formulation of linear programming problem is a must before we go in for a solution for LPP.
Thanks a lot for those valuable insights. Remember, I told you the reason we lose marks is because we skip writing a few steps here and there. Now, to sort out that problem, let's look at the marks breakdown for a few questions. A diet is to contain at least 400 units of carbohydrate, 500 units of fat, and 300 units of protein. There is a choice of 2 foods that are available. F1, which costs rupees 2 per unit, and F2, which costs rupees 4 per unit. 1 unit of food F1 contains 10 units of carbohydrates, 20 units of fat, and 15 units of protein. 1 unit of food F2 contains 25 units of carbohydrates, 10 units of fat, and 20 units of protein. You've guessed the question. Find the minimum cost for a diet that consists of a mixture of these 2 foods and also meets the minimum nutrition requirements. Formulate the problem as an LPP. Now suppose that the diet contains X units of food F1 and Y units of food F2. The total cost of X units of food F1 and Y units of food F2 is, you guessed it, rupees 2x plus 4y. Now let Z denote this total cost. This gets you 1 mark. Now since each unit of food F1 contains 10 units of carbohydrate, X units of food F1 will then contain 10x units of carbohydrate. Similarly, Y units of food F2 contains 25y units of carbohydrate. But the minimum requirement of carbohydrate is 400 units. Therefore, 10x plus 25y is less than or equal to 400. And this step gets you half a mark. Similarly, the total amount of fat supplied by X units of food F1 and Y units of food F2 is 20x plus 10y. And the minimum requirement is 500 units. Therefore, 20x plus 10y should be greater than or equal to 500. And you get half a mark more. Finally, the total amount of protein supplied by X units of food F1 and Y units of food F2 is 15x plus 20y. The minimum requirement of protein is 300 units. Therefore, 15x plus 20y is greater than or equal to 300, which gets you half a mark more. Clearly, x greater than or equal to 0 and y greater than or equal to 0. And a half a mark more for that. The LPP is now ready. Minimize the cost. Z is equal to 2x plus 4y subject to the constraints. 10x plus 25 greater than or equal to 400. 20x plus 10y greater than or equal to 500. 15x plus 20y is greater than or equal to 300. And the non-negativity constraints, which is x and y, are greater than or equal to 0. And we successfully score that last 1 mark. In today's episode, we only formulated linear programming problems, but we did not solve them. We shall do that later. Meanwhile, let me tell you an interesting story. The man who came up with the solution method for LP problems was George Danzig, who worked on logistics planning for the entire US Armed Forces. There were lots of equipment to manage, lots of troops to deploy. Hey, that sounds like a good place to use linear programming, right? In his school days, Danzig was a bright student. One day, he walked in late into the class and his professor had left a couple of problems on the board. Danzig thought it was homework. But it turns out that these were hard, unsolved problems. And he managed to solve them. Well, he was the only man to get rewarded for coming in late into the class. But you people better be punctual for your classes, okay? And that's all I have for you today. Remember, practice makes perfect. Always remember that. Goodbye and cheers.